Any questions? Let's jump in. Here we go. So what is Calc 3? So it would not be wrong to say that Calc 3 is a course in what's called vector calculus. Vector calculus. That would be an accurate title. There's other titles you could use, but one accurate title would be vector calculus. So if we're going to learn vector calculus, we certainly better know about vectors, right? So let's do a crash course in vectors. Very important intro here. So the first thing is vectors are really, the reference point for vectors are scalars. Okay, there's kind of, you could break all quantities in the world into two types, scalars and vectors. So scalars are quantities that don't have an associated direction with them. They're just amount, how much. That's what scalars are. So then vectors, they have a how much aspect, but then they also have a direction associated with them. So that's what we mean by vectors versus scalars. So scalars, there are quantities that just have magnitude but not an associated direction. So what kind of real world quantities don't have direction associated with them?
Mass.
Mass is a good one, right? So mass is just how much stuff. There's no, when you have a mass, there's no direction associated with it. Yeah.
Speed.
Speed is, right, so how fast you're going, right? What other things?
Temperature.
Temperature is a good one. There's no direction associated with temperature. Any others you can think of? How about geometry? Angle measure. Angle measure does not have direction, yeah. Area is a good one. Area is scalar. Volume is scalar. Okay, so these are all. And there's one common one, changing quantity that you haven't mentioned. So temperature we said. Mass you guys said. So like time elapsed, right? So like how much time has gone by since the starting point doesn't have direction with it. So time quantities are scalar quantities. We said volume. So those are examples. There are more, okay? So vectors then they would have amounts, they would have magnitude, but then they'd have an associated direction. Up, down, right, left, some direction in space. So what are some examples of vector quantities? Yeah.
Velocity.
Okay, velocity, right? So velocity is not only how fast, but in what direction? What else? Yes. Acceleration.
Jerk.
Okay, jerk, yeah. Torque, yes, absolutely. Torque has direction to it, and that's a strange one because as something goes around like this, what's the direction of the torque? It's actually perpendicular to the plane. We'll talk about that. But yes, that's. What about force? Force have direction? Yeah, it has how hard the push is and in what direction. Okay? So these are quantities that have magnitude and an associated direction. So force, what you guys say? Momentum is one, you guys didn't mention. Okay, so now in terms of, we're going to say displacement. Displacement is change in position. So I started here and I ended up at the door, right? That has a magnitude and it has a direction, right? So that's what we call displacement, change in position. So what would just the scalar part of that be? What would just the magnitude be?
Distance.
Yeah, the distance, right? So how far it is from here to there, regardless of direction, is distance. Okay, so we want to get our terms down. Displacement is going to be the vector. How far and in what direction? Distance is just the how far part. Okay? And then someone mentioned velocity as a vector. And so just the how fast part, the scalar, is speed. So when we say velocity, we'll mean how fast and also in what direction. And then speed will be, regardless of direction, just the how fast part. Like speed of light, right? The speed of light. Light just goes in all directions, right? So we're really only interested in the scalar value of speed. Unless it's a laser, right? If it's a laser, then you got direction with it. Okay, questions on scalars versus vectors? Okay, so how do we represent vectors? How do we draw them? We use arrows, right? So these are our representations of vectors. And so the direction the arrow points is the vector's direction, right? And the arrow's length corresponds to the magnitude. So which of these has the greatest magnitude? If these were all the same quantity, type of quantity as a vector, the one with the greatest magnitude would be? Second one, the least? Third one, right? Okay. And this is relative, right? So, maybe this is, 8 miles, right? We're not going to draw the arrow 8 miles long, obviously, right? So, but relative to this might be, this might be like 1.5 miles, and then this would be 8 miles. Okay? And then since those are vectors, that would be displacement, not distance, right? Okay, so the arrow has a tip and a tail. The tip, so from tail to tip is direction, right? That's the direction we're pointing. Okay, symbolically, when we use either a bold, you'll see them in textbooks and type print, you'll see a bold letter means a vector, but you can't write in bold. You can, but it's not convenient, right? So when you're writing, you can just throw an arrow on the top of a letter, and that signifies a vector. And you'll see them both ways in web work. You'll see it both ways in textbooks. Okay? But when you're writing, you can just throw a little arrow above the letter, and now you're saying it's not just a scalar quantity, but a vector quantity. Okay, questions on the basics of representing vectors? It's going to get harder, I promise. Okay, equal vectors. What are equal vectors? A vector has a specific direction and magnitude, but not a distinct location. So vectors are direction and magnitude, but not location. So, for instance, 5 people starting at different places and times, but all go the exact same distance, heading in the same direction. So that might look like this. So my displacement vector 1 is over here in the 3rd quadrant. My displacement vector 2 is up here in the 1st quadrant, etc. So are they the same vector or different vectors? It's the same vector. It's the same vector. Okay. So think about like a marching band, right? So these are all people in the marching band, and then for some part of the song, they march from the tail to the tip, and they all do the same direction and distance. So they're all really, their displacement is represented by the same vector, even though they're in different places. So we could just call them all D. Instead of having D1, D2, D3, D4, D5, just call them D, because they're the same. Does it make sense? Okay, so adding vectors. So here I got 2 vectors, vector A, vector B. What would it mean to add them? What you do then, it's represent the addition of vectors, you place the arrow's tip to tail. So you can move it without changing the vector, right? So we can move A so that its tail is at the tip of B. And so the easiest way to start with adding vectors is to think of displacement. So it's kind of like, I was home and then I walked to the park. Not working. There we are. Yeah, so the easiest way to think about this is in terms of displacement vector. It's just kind of like, I was home. Why isn't this working? Just works. There's this. Okay, so here's home. And so vector B might be like, my displacement from home to the park, right? And then vector A might be my displacement from the park to Walmart. Okay, so what would B plus A represent then? What would B plus A represent? If I first was at home, I walked to the park, and then I walked to Walmart. Yeah, so doing both of those in succession, the overall result of that, doing both together, would be starting at home and ending at Walmart. But like as the crow flies, right? Bypassing the park. So the sum of the single vector, the results is the same outcome as the original vectors applied in succession. So this is B plus A. The blue one is B plus A. So it's like, what do you if you did B and then did A, what would the result be? Well, it would be the result of starting from the tail of B and ending up at the tip of A. So what about changing the order of addition? So same vector A, but now undo that first, and then put the tail of B at the tip of A. And so then what is A plus B? What do you notice? Same vector, right? Same direction, same magnitude, whether you do A first or B first. So B plus A is the same as A plus B, just like it is in scalar addition, right? So vector addition is commutative, just like scalar addition is. Okay, subtracting vectors, little more dicey, but we can do it. So to subtract vectors, we can start by thinking of that as add. So for the add, the opposite vector. So what's the opposite vector? So example, B minus A. So instead of B, think of it as B plus the opposite of A. What is the opposite of A? Yeah, so same magnitude, but pointing exactly in the opposite direction would be the opposite of A. So here, this is the negative A vector. Same magnitude, opposite direction. And so then you would do what? B plus the opposite of A. You put the tail of the opposite of A at the tip of B and do the addition. So then this is B minus A. But that's just kind of a starting point, all right? So really, more usually or more often, we're gonna do it this way. We're gonna start by putting the vectors tail to tail. So that's a good start. But normally, when you're subtracting vectors visually, you don't do the opposite of the second one and add. Normally, what you do is you start with tail to tail. And then, so B minus A is going to finish the triangle, but then the question is, what direction is B minus A? Is it up and to the left or down and to the right? Well, we know it's up and to the left because we already did it, right? But if you hadn't done this, how do you know how do we think about that B minus, would it make sense that B minus A is up and to the right? So one meaning for subtraction is what? Final minus initial, right? Final minus initial. So if you think of this is a final minus the initial, then you're going to put your initial, your tail of B minus A at the tip of A, and then final at the tip of B. So that's one way to think of it. The other way to do it is to just try it and check with addition, right? So where do we see an addition problem there, right? So how is this? This is the sum of what two vectors? No, this picture, right? This picture, if you're only allowed to use these three vectors, B, A, and B minus A, how does this form an addition problem? Yes, sir?
Just connect the tip of the second vector to the tip of the first.
Yeah, but what we're saying is there's two ways to do that. You can go up and to the left and down and to the right. So we need to have a way to know that we've got the direction right. See what I'm saying? Yeah, so what addition problem do we have here? Yeah, so A plus B minus A equals B. And so does the math work out? So A plus B minus A. So then, does that work or not? If I do A plus B minus A, do I get B? Yeah, because the A and the minus A go away, and you're left with B. But if you had tried it the other way, so say you were taking a guess, and you're like, okay, maybe B minus A is like this. Then what would the addition problem be? It would be B plus B minus A. According to my picture, this is true. Right? Start here. B tip to tail plus B minus A is the same as just doing A. Now, does that work out? No. What do you get? 2B minus A equals A. No, that's why I chose red, right? That's why I chose red. Doesn't work. So, kind of two possibilities in this. Think of final minus initial. So your B minus A you want to be at the tip of B, and the tail to be at the tip of A, thinking of the difference as final minus initial. Or you can just give it a shot and check the algebra. It's got to work out. If this one works out, this one does not. Any questions on that? So yeah, subtraction is a little bit trickier to wrap your brain around. Okay, so vectors, when we represent a vector, we use components. And we use horizontal and vertical components to express a vector. So for instance, this vector u, there's a vector u, vector v. So the horizontal, so by component we mean what part of u is horizontal. And so do you see, as you move from tail to tip, horizontally, what happens? You decrease by 1. Do you see that? As you move from tail to tip. And what happens vertically? Move up how much? 2, right? So this vector u can be described as a horizontally -1 and vertically 2. And then what about v? Horizontally what? Horizontally plus or minus what? Positive 4. And vertically? Yeah, like -2, right? All right, so that vector u, so we use chevrons, like these angled brackets like this. I call them chevrons. I don't know what they could be called. But this is the vector -1, 2. So we describe that vector as its components. -1 in the x direction, 2 in the y direction. So v would be, I'm not talking in alignment with my slide, sorry. So what do those, this is really important, what do those vectors, what do those values represent for the vector u then? What does -1, how can we think of -1 in terms of the vector u and 2 in terms of the vector u? Yes, ma'am. Yeah, it's like, so, yeah, and so we want to save displacement for specifically displacement vectors, but yeah, that's the right idea. Like, isn't this -1 kind of like how much the x does what? Changes, how much it varies, right? How much x varies represented by this vector, and this vector, the 2 is how much y varies. So it's kind of like, it wouldn't be wrong to represent it this way. The vector components are like the variation in x and the variation in y taken together results in the vector u. Super important. Amounts of change, right? Amounts of change or variation, right? Amounts of variation. How much x varies, how much y varies. That's why vectors are mobile. Position doesn't matter. If I move this vector somewhere else, what are its components? Same, because the amount of change that that vector is representing in x and y does not change when I move that vector. So there's nothing about this starting point, right? There's nothing about the starting, what's the starting point? 3, 1. There's nothing about 3, 1 in that, the way we're representing that vector negative 1, 2. You see that? Nothing about 3, 1 there. Okay, so v is 4, negative 2. Okay, so another way to express vectors in terms of their components is in terms of what's called the standard basis unit vectors. What vector is that right there? What are its components? It's a very special vector, so that vector is 1, 0. And we call that I. That's the vector I. And the vector j is 0, 1. So these are called the standard basis unit vectors. So notice that you could write u then as negative 1 times I plus 2 times j. Because it'd be negative 1 times what? 1, 0 plus 2 times 0, 1. Negative 1 times 1, 0 is negative 1, 0. 2 times 0, 1 is 0, 2. And so then here's the beauty of having vector components. When you add vectors, you have apples to apples, right? You have your change in x and your change in y. So in the first vector, we change x by negative 1, and then in the second vector, we don't change x. First vector change y by 0, then change y by 2. So you can just, those are apples to apples and oranges to oranges. So you can just add those together and you get so you'll see both of these notations, but what I'm showing you here is it's not just two different labels for the same thing. They're mathematically equivalent. See that? I just showed it. This is a mathematical expression that's equal to this mathematical expression. It's not just two different labels. You could say it this way or you could say it this way. No, do the math. You get the same thing. Okay, so now we want to add them together. So vectors are mobile. Did I change the vector u by moving it? Nope. Tip to tail. And so then what am I setting up for here? Am I setting up for u plus v or v plus u? I'm setting up for v plus u, right? So the way I've drawn the picture, this would set up for v plus u. First v, then at the tip of v, put the tail of u. So I'm setting up to express or find v plus u, not u plus v, right? So what would v plus u be? Well, if we change by 4 first, and then we change by negative 1, what's the overall change in x? 3. 4 plus negative 1. And if I change by negative 2 in y, and then change by 2 in x, or 2 in y? 0. So that's the beauty of expressing vectors by their components. It's super easy to add them, because you can add changes in x and changes in y. And then you get 3, 0, and then we look at the picture and we just as a check. Visually, does that look like 3, 0? Yep, 3 to the right and 0 up or down. Okay, we can also express that as 3i, right? 3 times the vector 1, 0. That'd be another representation. So again, the length of the arrow represents the magnitude of the vector. So now I'm gonna start taking attendance here. I want you to find the magnitude of each vector. The magnitude of each vector, which means, in this case, the lengths. All right, that's a little task for you. You can work on it by yourself. You can work together, get help. And Young can help you, but I encourage, in class, I encourage you guys to collaborate. If you want to start off quietly, that's fine, but at least check your answers at the end, okay, at very least. Everyone got the information? I need to leave the screen to get to the attendance. Okay, and so this is how we represent magnitude. You put like absolute value bars around the vector, and that says forget about the direction, we just want to know how much. How far, how fast, whatever, but no direction. You'll also see them with double bars around vectors. That means the same thing. So whether it's single bars or double bars, they both mean we just want to know the magnitude of the vector. So what did you get for the magnitude of u? So I didn't tell you how to do this, but this is something that, hopefully by calculus 3 we're becoming problem solvers, right? We're doing this. Yeah?
Square root of 5.
How'd you get that?
I treated it like a hypotenuse and used the Pythagorean theorem.
Exactly. So we've got what? -1. Right, -1 and 2. We know that that's what those components are. So really, a vector is a hypotenuse of a triangle. And so then you can use the Pythagorean theorem, and you would have the square root of 1 squared plus 2 squared, and so the square root of 5. There we go. Okay. V, magnitude of V? Root 20, right? So you're going to get square root of 4 squared plus square root of 2 squared, root 20. And then V plus U, we're going to do square root and do sum of the squares. Yeah? No, just look at it, right? So don't do that. On that one, look at your vector first. Clearly, magnitude is. You just write it down, right? You just write it down. If you're going 3 directly to the right, then your magnitude is 3. Okay, so then given a vector, say any general vectors, let's call it V, then what would the magnitude be? Right, so you think of these are going to be the 2 legs of your triangle. Use the Pythagorean theorem, and so then you get, that's your general formula. Oops, magnitude of V, magnitude. And then when you do that, you just get a number, right? The amount, how much. I'll try not to write so low on the screen. But by doing these problems, you derived that, right? So you did the geometry, Pythagorean theorem. So then we say, oh, well, we could just generalize and write down the formula for the hypotenuse of a right triangle with legs x and y. Okay, any questions on magnitude? Oh, yes, please.
On the online homework, if it's something that, like root 20, would we have to put like 2 root 5?
No, so WebWork is very, very forgiving. You can put in expressions. So you could put in 4 times root 20 over 2 squared minus 2 root 5 plus 2 root 5. And they'll give it to you right. And so, and that being said, I actually don't do this, but when you're solving these problems and you get an expression that's going to give you the answer, put the expression in, because don't go to a handheld and punch it out. There's problems with that. You could make an error in your punch, or you could you don't know how many decimal places to round to then. But WebWork can be your calculator for you. Put in expressions like this, not dumb ones like this, but put stuff in like that, and then it'll give you a nice, if you do a preview instead of using an attempt, it'll give you a nice image of what you put in, and then it'll give you the decimal approximation, all that stuff, but it'll treat it as an exact answer, and it'll have all the decimal places you need. Okay. Any other questions? All right, so what would 1/4 v mean? So what would 1/4 do to the vector v? Yeah, so what about the direction?
The direction stays the same.
Yeah, so this is what's called scalar multiplication. If you multiply a vector by a scalar value, it messes with the magnitude of it. Except, so let's do, so 1/4 v, and v would be what? Or minus 2. So scalar multiplication, if you want a vector in the same direction with 1/4 of the magnitude, then you're going to want what? 1/4 of each of the changes, right? You're going to want 1/4 of the change in x and 1/4 of the change in y. So it feels like the distributive property. You can just multiply your 1/4 in. So 1/4 of v is 1 comma negative 1/2, and then 2u would be. So now what? So this is a vector that's twice as long or twice as much in magnitude in the same direction as the original vector. So that would mean twice the change in x and twice the change in y, which is -2, 4. And then to add, yeah, so change in x of 1, then change of x of -2 results in change of x of -1. A change of x of -1/2, and then the change in y of -1/2 plus a change in y of 4 results in 7/2. So does scalar multiplication always preserve the direction of the vector? There's a situation where it doesn't. Yeah, when your scalar is negative. So if we multiply this vector u times -2, then it would have twice the magnitude, but in the opposite direction, right? So then, I'll just try to, I don't have room to draw it. But it would be, I think, I end up not quite getting -2 though, but you get the idea. So it would be -2u would be twice as long as u, or twice the magnitude of u in the exact opposite direction. So in general, scalar multiplication doesn't change the direction unless it's negative, and it just flips it, changes the direction to the other, exactly the opposite direction. Okay, questions on that? Oh, shoot. A little bit behind. Okay, so initial and terminal points. So if I had fixed locations, say I had 1, 3, point P is 1, 3, and point Q is 4, 1.5. You can define two vectors from these 2 points, right? You could find the vector from P to Q, and also the vector from Q to P. So if I want to define the vector from P to Q, and there we go. So from P to Q would be represented, so we can do this. We can write PQ with the arrow over both, and that represents the vector with tail P and tip Q. So what would the component notation be for PQ? What does that mean again? What does it mean? How much x changes, right? How much x varies? How much does x vary? Positive or negative? X. Positive 3, right? And how much does y vary? Negative 1.5, right? So x varies by 3, y by negative 1.5. So if the numbers weren't so easy to do in your head, what is it that you're doing to get those changes? Final minus initial, right? You're taking the final value of x, subtracting the initial value of x, So this really was, what you did fast was 4 minus 1. And this is final minus initial, 1.5 minus 3. So use the meanings to help you, right? You know that, so how do I get that component? Well, it's going to be how much x varies. So x varied by 3, and if the numbers were harder, I'd get that by final value minus initial value. So then QP would be what?
-3.
Yeah, it would just be reversed, right? Because now you'd be doing what? 1 minus 4, final minus initial, and 3 minus 1.5. And that would be, so it's equal, and those are like equal and opposite vectors, right? Same magnitude, opposite direction, QP and PQ.